without further ado, Todd, over to you.
Well, thanks very much, Lang, and thank you to all the attendees for joining. I tried to select topics that are not too basic so that those who are familiar with vapor intrusion will find this interesting, but also provide enough coverage that those who are new to the field will not be lost in the process. So I hope I've struck that balance right. Vapor intrusion is the exposure pathway through which volatile organic compounds that are released in the subsurface can diffuse laterally through the vadose zone or dissolve in groundwater and subsequently vaporize to the unsaturated zone, then move upward into buildings. And it's complicated because there's a lot of different types of buildings, different types of building foundations, different sizes of buildings, and the properties of the different chemicals. L-naples and D-naples are light non-aqueous phase liquids, and dense non-aqueous phase liquids behave differently in the subsurface, and the geology of each of the sites is a bit unique. So it's not necessarily a straightforward thing to assess. Today, I'm going to talk about some basic concepts, typical assessment methods, some of the common challenges and emerging solutions, and an evolution of mitigation options. And we'll begin now with basic concepts, which include the following: a little bit about the dose relationships, the attenuation factor, conceptual models of the sources, and the root causes of variability, and some unique factors for different types of buildings, ending up with a discussion of the taxonomy of different vapor intrusion sites. When we perform risk assessments, we usually make assumptions that people consume something in the order of a couple of liters a day of water, whereas people inhale around 20,000 liters per day of air. And because there's such a large volume of air coming into the body, and the lungs are a very efficient mechanism of transferring gas into the bloodstream, I mean, that's what they do with oxygen, we need to have concentrations in the gas phase that are much, much lower in order to get a total body dose that's at the same level. And this is the most important thing that makes vapor intrusion assessment a challenge. We have such low target levels that oftentimes we're down in the range of background concentrations. We have to be very fastidious about cleanliness of sampling equipment to avoid carryover and sample contamination. And everything just gets more difficult when your target concentrations are that low. Our simplified conceptual model, in the very beginning, people were wondering, can we predict the concentrations inside the building from some measurement of concentrations in groundwater, or maybe the concentrations in soil vapor? And it was understood very early on that the indoor air concentrations would be lower because of dilution. The buildings are ventilated. For some chemicals, degradation. And depending on the geologic conditions, there could be limitations to the upward flux of chemicals from below. But that led to the question of exactly how much attenuation would we expect. And some of the early work was done with some simple calculations that led themselves to spreadsheet type of mathematical models like the Johnson and Ettinger model, where alpha, which is this factor of attenuation, was calculated as a ratio of a whole bunch of different parameters. With any mathematical model, the output is only as good as the input, and if you have some uncertainty in each of these parameters, then you'll have some uncertainty in the calculation. So there are some people who consider the Johnson and Ettinger model to be a useful screening tool, others who have less trust in it. Those who have less trust in it tend to fall back to empirical data. The US EPA has compiled empirical data where there have been measured concentrations of VOCs in groundwater and indoor air, soil gas in indoor air, sub-slab soil gas in indoor air, and even crawl space in indoor air. And they've calculated the ratio of those concentrations and plotted them up in a frequency distribution, and have relied on the 95th percentile values to, derive screening levels that they consider to be protective in most cases of the vapor intrusion pathway. But if you look carefully, the difference between the 95th percentile and the 5th percentile is, up to a few orders of magnitude, a couple of orders of magnitude, a couple of orders of magnitude. So there's uncertainty in evaluating the indoor air concentrations from subsurface concentration measurements, regardless of whether you're using a mathematical model or empirical attenuation factors. And there's certainly some variability in the attenuation factors from site to site. This is a chart that shows those same kinds of box and whisker plots for a variety of different sites. And you can see the attenuation factors are higher at some sites and lower at others. And so this really gets down to the question of what's the root cause? What is it that's causing these differences in these values? So there are several factors. One is the position of the source. If the source of volatile organic compounds is above the water table, then there's a much more direct pathway to the overlying building. If it's below the water table, then chemicals first have to dissolve into water and then permeate across the capillary fringe, then vaporize before they can migrate up. So a source below the water table poses a much lesser risk of vapor intrusion than a source within the unsaturated zone. And the position of the source with respect to the building is also important. If there's a source outside the building footprint and down gradient, then chemicals can still diffuse backwards through the vadozone in response to the concentration gradient, but they're moving in the opposite direction in the saturated zone in response to the hydraulic gradient. So that scenario will less likely pose an indoor air quality risk than certainly a source directly below the building that can migrate directly upwards after diffusing laterally through the vadozone, or a source that's outside the building but up gradient that can be carried underneath the building through groundwater and subsequently vaporized. Chemicals can also migrate considerable distances through the unsaturated zone, especially where the vadozone is thick, and this occurs more often in arid climates, and I know there are certainly portions of Australia that are very arid climates. So you may have a deep water table, and off-gassing from groundwater may not be a threat if it's deep enough, but lateral migration through the vadozone can be a concern. It should be not be ignored. Generally, concentrations of concern could extend up to 100 meters or more from a source area, but usually not much further than that. If you have VOCs that have dissolved in groundwater and are migrating laterally, they can off-gas over some considerable distances. There are some sites where there have been vapor intrusion impacts up to 5 kilometers from the source area. If there's enough in the way of infiltrating rainwater that causes the groundwater plume to progressively get deeper and deeper and more removed from the water table, then there's less off-gassing to the vadozone. So a diving plume or a freshwater lens can inhibit vapor intrusion quite considerably. That works only as long as there are not significant water table fluctuations. A diving plume can subsequently be exposed if the water table falls during a drought condition, leaving behind some VOCs in tension saturation in the unsaturated zone that can subsequently vaporize. So all of these factors affect the susceptibility of one site to the next for vapor intrusion. And then there are environmental factors. Here's, for example, a chart of building under pressurization versus wind speed that was measured by the folks at Arizona State University, Paul Johnson et al., at a site in Casper, Wyoming. At low levels of wind velocity, the building pressure varies around a fairly narrow range, but as the wind speed increases, the building goes under vacuum. And the reason for this is the same as the reason why airplanes fly. When the wind goes very quickly over the wing of an airplane, it creates lift. And when wind goes over the roof of a building, it creates suction as well. And so you can see that you can get very strong underpressurization of a building if the wind blows. And we know that, winds blow. We also know that winds don't necessarily blow consistently. So you can have wind gusts where the building pressure is fluctuating backwards and forwards, sometimes with considerable variability. So when we measure the pressure differential across the floor slab of the building, we often see this kind of a signal where the magnitude of the fluctuations can be several pascals or even tens of pascals in response to wind changes and other things. They can sometimes average, like you see in the blue color, around a neutral value, and sometimes average around a slightly depressurized or pressurized value, depending on other factors such as temperature differences and mechanical fans that are either blowing in excess of air into the building or withdrawing in excess from the building. But you can see that there's a high degree of variability, and it occurs with a few different frequencies. So there's a certain frequency of variability here that might be something like hourly or several hours in duration, and then there's a higher degree of frequency that's occurring almost on a minute type of scale, with occasional peaks that can be quite large and swing backwards and forwards in both directions. So the effect that has, particularly when coupled with pathways of entry into the building, this is an image of concrete floor that's theoretically, been sealed with a sealant, caulking, but sometimes those crack and are no longer effective, or natural soil that has dried out and desiccated. And we certainly know that underneath buildings, the building basically acts like an umbrella, and so the soil underneath the building doesn't see rainfall and infiltration anymore, and so the soils generally tend to dry out underneath the building. So with these sorts of pathways and those sorts of pressure differentials, what we get is an erratic entry of vapors into the building that results in a high degree of variability over time. So this chart shows data that was collected over 4-hour average intervals from a house purchased by Arizona State University adjacent to Hill Air Force Base in Utah. And you can see that the peak concentrations are at least 3 and almost 4 orders of magnitude higher than the minimum reporting limit. There are instances where there are very few detections with sporadic detects and instances where there are generally detections with sporadic non-detects. So there's a high degree of variability, some seasonal trends perhaps, but generally speaking, not a very good ability to predict the concentrations based on analysis of the correlations of this data to temperature and pressure and wind speed and other things. So it's fairly complicated. It raises the question of how many samples do we need to estimate the long-term mean. If what we're interested in from a risk assessment perspective is the health concerns over a 25 or 30-year exposure duration, and we see this kind of variability, is one sample enough? Is a dozen samples enough? Do you need more? And it's also a question related to the duration of the samples. We generally collect samples over some period of time instead of instantaneous time-weighted average sample. For industrial hygiene, the time-weighted average is usually around 8 hours because that's a working shift. For residential scenarios, sometimes 24 hours because that's a diurnal cycle. But there are other durations that can be evaluated as well. In addition to the temporal variability, there's spatial variability. This is data from the California Department of Transport site in Colorado. There was a release of chlorinated solvents at the CDOT facility, high concentrations in groundwater nearby, the direction of groundwater flow in this vicinity, and eventually concentrations were measured to be quite low, and the plume was considered to be mapped. But what was not recognized at that time was that there was a bedrock knob in this area, and the groundwater was diverted around that feature through another channel, and an entire plume of VOCs and groundwater existed to much greater distances than were originally considered. This entire lobe of the plume was identified by the fact that some indoor air concentrations that were elevated were detected in these homes, and additional sampling detected in more homes and more homes and more homes. So at this particular site, houses were used almost as flux chambers to map the groundwater plume, which was to everybody's chagrin after they thought that the plume was originally mapped to be just in a short distance. So spatial variability depends on geologic heterogeneity. We as hydrogeologists are used to dealing with geologic heterogeneity, but it does have a big impact on vapor intrusion assessment as well. There are some factors that are unique to large buildings. We're doing a lot of work now for the U.S. Department of Defense. Large buildings typically have a slab-on-grade type of foundation, but the floor slab can be of different designs and thicknesses, can have coatings or not, and coverings, expansion joints, or utility corridors running through the floor. Some have granular fill below the floor, and some are placed on native soil that can have different permeabilities. So the routes of entry are different from one building to the next. Large buildings are also typically ventilated with rooftop air handling units. Each of these little squares is an air handling unit that blow air into the building after heating or cooling it, depending on the weather. And that generally creates a bit of a positive pressure for the building, although kitchens and bathrooms will always have exhaust fans, and there can be fume hoods and other such features that are exhausting gas from the building as well. Usually the air exchange rate for large buildings is dictated by building codes and controlled in a more stringent way than with residential buildings. And then there's tall buildings. If you have a tall building and there's a temperature difference between indoor and outdoor, then the building will have a stack effect. If, for example, it's colder outside and warmer inside, hot air rises, And what that does is it creates a pressure differential inside the building that makes for positive pressure near the top and therefore negative pressure near the bottom. Anytime you enter a building that has revolving doors, you'll know that that building is tall enough that there's a significant stack effect, and that's why the revolving door is there, to prevent huge volumes of air from being drawn into the building and, increasing the bill for heating or cooling the building. Furthermore, buildings that have elevator shafts can very effectively distribute the air vertically throughout the building. So that's something to be aware of when it comes to assessment if there's a release of VOCs near a tall building. Petroleum hydrocarbons really are different because they degrade very quickly. So this is a map of hydrocarbon concentrations that show reduction of one order of magnitude, then another order of magnitude, another order. So very rapid decrease in concentrations in the region where oxygen concentrations become high enough to give the microbes what they need to be able to degrade the hydrocarbons. If you've got a very shallow source, you can have vapor intrusion entry. As you get to deeper sources, there's enough opportunity for the microbes to degrade the chemicals to levels below concentrations of concern. And as a result, separation between the source and the building becomes one of the most important factors. And the presence of oxygen is also one of the keys. So as a result of the differences from one site to the next, one size does not fit all when it comes to vapor intrusion assessment. So moving from left to right across the top here, chlorinated solvents are mobile and resistant to degradation. So they pose a greater risk of vapor intrusion than hydrocarbons, which degrade, or than semi-volatile organic compounds that tend to be pretty highly absorptive and therefore not very mobile in the subsurface. And for the chlorinated solvents, the source in the vadose zone below the building is a greater concern than a groundwater source is a greater concern than a vadose zone source outside the building footprint. For hydrocarbons, a shallow source is a much greater concern than a deeper source. And if you've got a low concentration in dissolved plume, then you probably don't have a problem at all unless it's almost directly in contact with the building. And for semi-VOCs, you really need to have a shallow source directly beneath the building before you're likely to have a concern for vapor intrusion. So because each of these have a different potential for risk, they can be assessed using some different tools in the toolbox and perhaps prioritize the different priorities. Advance to the next slide then. At least in North America, what we found is that the last decade or two worth of vapor intrusion assessment has resulted in some persistent misconceptions. Some regulatory agencies are asking for every assessment to include all of the analytes that exist on the EPA Method 215 analysis list, including a dozen or so that are not even toxic and several that are just so commonly present from consumer products and building materials that might not even be present in the soil or groundwater at the site, but they just end up creating a bunch of red herrings. Some regulators feel that they can't make a decision without indoor air quality data, despite there being conditions where there's really not a chance that anything could be making its way into indoor air, and that in many cases can be demonstrated if there are, for example, geologic barriers that are, wet clay, for example, that vapors just can't migrate through. There are some regulatory guidance documents that say you must minimize the purge rate and volume for soil gas samples, and we've shown that that's not the case. As long as you've got well-sealed probes, then you can collect samples at higher flow rates or higher volumes with no bias. Many of the regulatory agencies are applying residential attenuation factors for commercial buildings, and they're really not the same. Commercial buildings have a higher air exchange rate usually that results in lower attenuation factors. In many cases, the reporting limits that are required for laboratory analysis are as low or lower than background levels, and therefore compounds that are not attributable to vapor intrusion will almost always be detected, and that requires explaining often to a non-technical audience of building occupants or owners. There's a common misconception that you can always just throw in a radon mitigation system and just deal with the problem in an inexpensive way. It can be inexpensive, but it's not always. Another misconception is that, summa canisters are the only way to collect samples. it's a gold standard or something like that. There are some limitations that I'll go through in a minute with their use and application. Misconceptions that vacuum below a floor slab is needed for effective mitigation. That's derived mostly from the radon industry. Some people follow the regulatory guidance documents as if they're foolproof, but they're not. There are opportunities for any assessment method to be inappropriate for any particular set of site conditions because there's enough combinations and permutations of different conditions that it's not one size fits all. A lot of people look at every sample as if it's completely unbiased, but every sample is just an estimate of the true concentration. And many are treating screening levels that are designed to be, very conservative and highly protective, as if they're bright lines above which mitigation is immediately needed. So those are some of the persistent misconceptions and challenges that have been difficult to shake and have been haunting us for decades. Next slide.
Todd, I might suggest, if you don't mind, it might make it easier for the rest of the presentation. Try to rejoin via the original email link, and that might actually allow me to give you control again and just facilitate the rest of the slides.
Okay.
And in the meantime, I'll continue to advance for you.
Okay. I'm just going to give this a second. Telling me my meeting will start shortly. And you can still hear my audio, can you?
Yeah, we can still hear your audio, okay? That's coming through clearly.
Okay. Yeah, it's loading up to, it's at 57%. It'll be there shortly. What slide are we on now, Lang?
We're on slide 25, so it's just one of those roadmap slides for typical assessment methods.
Okay. So the next thing we're going to talk about is how vapor intrusion is normally assessed. And I think I'm back now. You can probably try giving me the presenter control.
Okay,
I'll go over this part fairly quickly in the interest of trying to capture some time, because what's in this next section is, an overview of how vapor intrusion is typically assessed, and I'm going to guess that most people know something about that already. I'm not
I'm just waiting, Todd, to see if I can
why don't you
hand
just
you
go
through.
ahead by one slide.
Updated you as a web attendee yet, so
okay.
As soon as it does, I'll let you know. But I'll just keep advancing slides for you in the meantime.
Okay, go ahead then to the next slide. Go ahead then to the next slide.
Okay, do you see the SUMA canister slide in front of you?
I do. Mm-hmm.
Okay, so next slide.
I mentioned earlier that SUMA canisters aren't necessarily the simplest thing. The procedure is fairly complex with a lot of wrenching that needs to happen, and if the wrenching isn't done to the right pressure, there can be leaks. And there is some special training that's required to just make sure that valves get on properly and vacuums are measured correctly. They need to be cleaned and certified, which costs money. They're bulky and expensive to ship and handle. Usually they can't be used to collect a sample longer than about 24 hours. It'd be fairly costly. And when you try to collect samples for compounds heavier than about naphthalene, they go into the can, but they don't come out very well. And so you have a negative bias in their concentrations. And from a visibility perspective, it looks somewhat like a bomb. We've had people call the police when we've sampled outdoor air with them. The most common alternative is automatic thermal desorption tubes, which is basically a tube about the size of a cigarette that contains an adsorbent. You pump gas through it, and you measure the flow rate and the time to get the volume. The laboratory quantifies the mass, and you divide that by the sample volume to get a concentration. This can be extremely accurate and precise, and it still has some limitations. It's not that easy to collect a sample longer than 24 hours because eventually the sorbent gets saturated and compounds start to break through. And the pumps that are used are generally run by batteries that really don't last much longer than 24 hours. So if you're going to do that, you need to depend on a reliable electrical supply. And as you can see from today, electrical systems aren't always that reliable. So we'll move forward to the next slide then. One common problem with both of them is that there's a limit to the duration of the sample that can be collected. If you talk to somebody in the radon industry, they refer to a sample of 90 days duration as a short-term sample. And, they're often collecting samples over a period of a year to get a better time-weighted average concentration, more representative of long-term averages. Move forward then. Yeah, so why do we collect a 24-hour sample? And the answer is because we can, not necessarily because it's the right thing to do. And I think the next 2 points, if you click again, are, neither of the existing methods, TO15 or TO17, are well suited to the longer intervals. But the folks in the radon industry don't even consider anything less than a 72-hour sample duration to be representative. Move forward then. Right.
Okay. Right.
Okay.
The...
So we typically collect sub-slab samples by drilling a hole through the floor, connecting up a cement canister, and after purging, collect a sample for analysis. That's usually a pretty small volume sample, 1 liter, maybe 6 liters. I'll try to argue later that we can get more information from drawing a larger volume. Move forward. And collect soil gas samples with a variety of techniques, from either through the floor of the building or outside the building nearby. Carry on. But with soil vapor sampling, I could give a talk of almost an hour duration on just all the different things that can go wrong. If you're sampling groundwater and you have a leak, you get a puddle. If you're sampling soil gas and you get a leak, you can't necessarily see, hear, smell, touch, or taste it. So this blue plastic bin that's upside down on the ground is filled with helium, and the samples are first screened for the helium concentration to make sure that there's no helium in the sample before a sample is collected, which requires a whole bunch of apparatus. And once you start doing all that, it's fairly time consuming. It's definitely a 2-person job, and that just ends up increasing the cost of it all. Next sample. When it comes to assessment for petroleum hydrocarbons, as I mentioned earlier, sometimes the most important information is the oxygen distribution. So a GEM 2000 landfill gas meter can be used to monitor oxygen, CO2, and methane in the field, and often give you very useful information, certainly much more quickly and much more affordably than laboratory analysis of VOC concentrations. Often methane is the compound of most mobility and greatest oxygen consumption. So a photoionization detector won't detect methane, but a flame ionization detector will. So a slightly different set of kit is usually required for assessing petroleum hydrocarbons. Next slide. And the compounds of concern include benzene, trimethylbenzenes, ethylbenzenes, that have risk-based indoor target concentrations. You can see these slides are kind of messed up, but for benzene, that should be 0.31 micrograms per cubic meter relative to a saturated vapor concentration of about 300 million. So there's a huge difference between the maximum concentrations and the concentrations of concern, which creates a bit of a challenge for labs because they don't have linear ranges of their analyses that are that broad. Next slide. fortunately, there are models that have been put together for evaluating the transport of petroleum hydrocarbon vapors. The Vapour model is available from API as a free download at the web link that's shown at the bottom of the page. And it's just about as easy to use as the Johnson and Ettinger model. It's based on that, but it adds first-order degradation and includes a graphical user interface that allows a pretty rapid screening of site conditions to see whether there's likely to be a problem or not. And the vertical profile of oxygen and hydrocarbons can be compared between the mathematical model and the field data to give some degree of comfort that the site conditions are consistent with expectations. Next slide. And the unfortunate reality is anytime you collect a sample of indoor air, you will certainly detect concentrations of volatile organic compounds, and often the same compounds that we're concerned with. This is a chart of the percentage of detections of volatile organic compounds in indoor air samples in properties that are not associated with contaminated land. And you can see that the BTEX compounds at the top are virtually always detectable from consumer products and building materials. The same goes for carbon tetrachloride and chloroform and tetrachloroethylene, 1,2-dichloroethane. And those compounds have risk-based target concentrations that are as low and often lower than the background concentrations, which is, why it's always difficult to assess vapor intrusion, and you can't just rely on indoor air sampling alone. Next slide. This is just an example of the detection frequency of 1,2-dichloroethylene at Hill Air Force Base. There was an increasing frequency of detection over time, and that was subsequently attributable to, just click the button again, Lang. Go forward again.
I think there's just a little lag between the click and the refresh on the screen.
Yeah, so they found 1,2-dichloroethane was coming from plastic ornaments that were manufactured in China and resulting in indoor air concentrations above the risk-based target concentrations. So scary Christmas decorations. Next slide. So it wanted to be about this point halfway through, and we're now 3/4 of the way through time-wise, so I apologize in advance for that. I'm going to try to move quickly through some of the common challenges and emergent solutions as well. Let's go forward to the next slide. The challenges I think I've laid out, that we have background above the risk-based concentrations, temporal variability, access interruption and disruption. If you click forward, those are all problems with indoor air sampling. But if indoor air is well mixed, then we don't have spatial variability. At least the indoor air sampling methods are fairly consistent, and regulators tend to trust indoor air. There's not extrapolation from indoor air to the point of exposure. With soil gas, the background concentrations are usually not a concern. Temporal variability is much less of a concern. Access and disruption isn't as bad as going into people's homes, but there's spatial variability, less consistent methods, and therefore less regulatory cost. Groundwater is similar, the first three categories, to soil vapor. Generally has more consistent methods and therefore more regulatory trust, but there's still the issue of extrapolation to the indoor air concentrations and the uncertainty of the attenuation factor. For all of these media, there's conservative risk-based screening levels that make for frequent exceedances, and they're generally fairly expensive. So that's a pretty good roadmap of the challenges. And the next slide, we're going to run through some of the emerging solutions. So there's ways to handle temporal variability and spatial variability in background sources and preferential pathways, and improving the mitigation options. And that's the focus of the remainder of the talk. We'll begin with a discussion of long-term passive sampling. Like folks in the radon industry, you can collect samples over a longer period of time and have less in the way of temporal variability in the results. We just finished a 5-year study funded by the U.S. Department of Defense looking at 5 different types of passive samplers. The concentration C0 measured with a passive sampler is the mass that gets absorbed divided by the sampler's uptake rate and the sample duration. What's interesting about that is if you leave it for a longer duration, you can get a lower concentration, without any additional increase in the analytical cost. They're also very simple to use, really no moving parts, and therefore very easy to train somebody to use. They're also smaller and more discreet, so they have a few advantages over the routine sampling technique. Move forward. So we did chamber testing in a laboratory chamber and tested 10 different VOCs at a variety of different values of humidity, temperature, sample duration, air velocity, and concentration. 24 chambers with 5 samplers each and triplicate with 10 VOCs gave us 3,600 data points. Move forward. So just to give an example of the kind of performance for trichloroethylene and tetrachloroethylene, these are again box and whisker plots for each of the different sampler types across the bottom and the concentration along the vertical axis. In the range between the blue lines, we met the performance criteria, and you can see for most of the samplers, very narrow range of variability. Move forward to the next slide. And this is just a broader list of contaminants across the bottom. And you can see that there's little variability when you start throwing in all the different conditions of humidity, temperature, velocity, concentration, and exposure duration. But still, most of the instances within the control lines of our acceptance criteria. And for 4 different sample types over a range of up to 6 orders of magnitude and concentration, with indoor air, outdoor air, subslab, and soil gas samples, we have pretty encouraging results. The passive samplers definitely have a place. We've also made advances with passive soil vapor monitoring. In the past, people have considered it to be something that can measure mass only, but not concentration. We've now a series of 3 papers that derives the mathematical basis, the laboratory testing basis, and the field testing basis for quantitative passive soil vapor sampling, and have quantitative results that agree with precision and accuracy similar to conventional active sampling. Next slide. The Waterloo membrane sampler is a product that Geosyntec is bringing to marketplace. It was developed at the University of Waterloo and is being commercialized through our laboratory serum in partnership with a couple of different laboratories. In Australia, Leader Consulting is providing analysis of these samplers, and we've used them at several sites in Australia already. Next slide. All passive samplers have a few advantages over conventional samplers. The Waterloo membrane sampler has a few specific advantages over other passive samplers, and that it can be used to evaluate less common compounds. The uptake rate of the sampler is proportional to their elution time in a chromatography analysis, and they don't need to be calibrated with individual chamber tests as a result. It can do total petroleum hydrocarbons. It resists the effect of moisture because the membrane is silicon rubber, and that's what you use for caulking bathtubs. It's quite water resistant. They're insensitive to high wind velocity, so it can be used in basically any kind of velocity environment, including venting pipes for SVE systems or Sub-Slab Venting systems. And if the next emerging solution is building pressure cycling, if we go forward, the idea behind this is if you deflate a building, then you'll induce vapor intrusion, and if you inflate the building, then you'll reverse that effect. If there are chemicals entering the building, they'll have a different concentration under those 2 conditions. This is a set of data for trichloroethylene and benzene. We measured concentrations in the subsurface and used the attenuation factor to predict the indoor air concentrations, which are shown in the second column for each of these 2 charts. And then we measured the indoor air concentration before pressurizing the building, and then measured again after pressurizing. So for trichloroethylene, the predicted concentrations matched up with the pre-mitigation concentrations, and after pressurizing the building, the concentrations dropped. Whereas for benzene, the concentrations that we predicted were much lower than what we actually measured under either the pre-mitigation or the post-mitigation scenarios, both of which matched up with the outdoor air concentration. So it's pretty clear that the source of benzene was outdoor air, and the source of trichloroethylene was in the subsurface. And this is work we've been doing since back in 2004. If we're dealing with spatial variability, we have a couple of different techniques for that. One is referred to as high volume sampling. The other is multi-increment sampling. We move forward to a map of a large building that's 600 feet by 1,100 feet in dimensions. It has underneath it 4 or 5 different volatile organic compound hotspots that was initially characterized with about 130 conventional sub-slab samples. I have to beg the question as to whether that's necessary to collect that many or whether maybe they should have collected some more. So how do we go about dealing with buildings this size? We'll move forward. One concept is just collect higher volume samples instead of a 1 liter sample. And to put that in context, if a worker breathes 20,000 liters of air a day over a 25-year period, that's over 100,000 liters of gas. If the volumetric flow rate of soil, Q soil, into a building is around 5 liters a minute over 25 years, that's 66 million liters of gas. So why do we collect a sample of 1 liter? Why not collect a sample of 1,000 or 10,000 or 100,000 liters? It would be probably more representative. So we can do that, and we'll show how we do. And then samples can be collected in increments, and that's something that's common in soil sampling for metals analysis. We've done some research in that way as well. If you divide your grid up into rows and columns, the intersection of the column, if you composite along a column and one column has a higher concentration than the other columns and you composite along rows and one row has a higher concentration than the other rows, the intersection of the highest row and the highest column is likely to be a hotspot. So let's move forward then. Here's a large building, and we've got samples in columns A, B, C, D, E, F, G, H, and rows 1, 2, 3, 4. And we also have 6 different high volume sample locations, 1, 2, 3, 4, 5, 6. The collected samples using a variety of different field techniques that I'm not going to go into a lot of detail on here just because of time. The results for the high volume sampling show concentrations that diminish between high volume sample location number 3, which had the highest concentrations, and number 6, which is the next lowest. Pretty much all the other locations are less than a part per million. We see that the concentrations in each of these locations didn't change much as a function of the volume purged. So whether we purged just a small volume or 80,000 liters, we had very similar concentrations. Just a gradual decrease in concentrations, which is attributable to the fact that the floor is not perfectly sealed. So the larger volume we pull, the more indoor air results in dilution. And I'll get into how we calculate that in a minute. By reversing the fan and blowing into the subsurface instead of sucking out of it and adding some helium, then you can monitor the arrival of helium at remote locations and work out the distance over which samples were collected during the initial high volume sampling stages. This is 2 sets of helium data, one showing concentration versus time at a distance of 17 feet and another at 79 feet away from the point of injection. And you can see that the arrival is measured in seconds. It really doesn't take that long for the helium to travel. So the samples can be collected from quite a significant distance away over the course of an hour. Next slide. The multi-increment sampling showed the numbers across the top as the concentrations in the columns. And you can see they're less than 1 microgram per cubic meter for all of the first 5 columns, and then much higher concentrations for the next 3 columns. And in the rows, the second row had the highest concentration. So next click. It's really the intersection of the hottest row and the hottest column that you would expect to have the highest concentration. And that's indeed the location where high volume sample 3 showed the highest concentrations as well. So let's talk now about background sources. If you detect multiple chemicals, then you can plot the concentration of one chemical against the next and see whether samples from different media match up. For example, this is methyl butyl ether versus benzene. And you can see that the indoor air concentrations, the soil gas concentrations, and the ambient air concentrations not only have a similar ratio of one to the next, but also similar magnitudes. In fact, the soil vapor concentrations are actually lower in terms of benzene concentration than the indoor air concentrations. So this kind of a portrayal of the data is more informative really than just comparing the concentrations to screening levels. In this case, the benzene concentrations are above the screening level. So if that's the only comparison you did, then you'd come up with potential concern. But if you're looking at it from a cause and effect relationship perspective, then that would not be a concern. And you can carry that forward on the next slide by plotting 3 different chemicals at the same time. On the left-hand side, you can see that the soil vapor concentrations are all plotting in the upper left corner, whereas the indoor and outdoor air concentrations are all plotting down in the bottom central part of the diagram. And on the right-hand side, there's 5 different axes for paraffins, isoparaffins, olefins, aromatics, and nitrosamines, and different samples showing different configurations for each of those as a way of assessing whether or not there's a relationship between the source and the indoor air. So that's one method. Another method is the building pressure cycling, which I've already spoken about, but I'll show another set of data. The building pressure cycling, if there are multiple chemicals present, go forward. I'm just waiting for it to refresh. You should be seeing a slide now that shows concentrations over time for a variety of different chemicals. Yes, 1,1-dichloroethene dropped very dramatically and stayed low. All the other chemicals didn't really change over time. And that's an indication that all those other chemicals were from sources inside the building. Next slide. The pneumatic testing and leakage analysis can be used to evaluate preferential pathways, particularly the amount of leakage across the floor slab, in much the same way as a groundwater pumping test analysis. You can use a pressure transducer and data logger to monitor the subfloor vacuum, and go forward. The signal has this kind of a shape to it when you turn the fan on and turn the fan off. Notice that all of this data was collected within the course of a couple of minutes, and that there's a much stronger signal at the closer distance, the red data, than the blue. This can be analyzed using standard groundwater pumping test data analysis after correcting for the density and viscosity of the fluid. The Hantush-Jacob-Leaky aquifer analysis dates back to 1955, so this isn't really that new a science. Next slide. So when you take that data and put it into a mathematical model and fit the curve to the data, you can see the data, which are the squares in the model, which is the blue line, match up quite well for both the drawdown and recovery. And through that curve fitting, we derive the values of transmissivity and the leakance, the R over B value. The leakance is the permeability of the floor, and the transmissivity is the horizontal permeability of the material below the floor. Next slide. From that, we can calculate the volumetric flow rate of soil gas into the building, which is the pneumatic conductivity times the pressure gradient times the floor area, as long as we've measured the pressure gradient across the floor. Next slide. And we can also calculate the profiles of vacuum versus radial distance, of the soil vapor velocity versus radial distance, the travel time to get to the point of extraction versus radial distance, and the proportion of flow that's coming from the subsurface compared to the proportion of flow that's coming from leakage. And all of this is useful information for understanding the high volume sampling test results or designing an optimized mitigation system for below the building. Next slide. So we'll talk a little bit now about evolution of mitigation options. The conventional method for mitigation is Sub-Slab Depressurization that was basically developed for the radon industry. Points immediately below the floor of the building are depressurized with a fan, and as long as there's a downward pressure gradient, then there can't be upward migration. And that works fine for domestic residents if you've got a fan that only costs a few $100s that draws only $100 a year worth of electricity. Whether it's over-designed or not, that's okay. Next slide. You can improve the condition by making a permeable floor. Aerated flooring is something that can be achieved with these plastic forms that basically allow the concrete to set with an airspace below it. and you can ventilate a much, much larger area with a much, much smaller fan and therefore be more energy efficient. Next slide. And that can be done at a variety of different scales. If there's an existing building, then you can use forms that are lower profile so you don't lose your ceiling height. Next slide. And there's a difference between sub-slab depressurization and sub-slab ventilation. For radon, the source is immediately below the building, but for VOCs, the source is usually at some depth. So if you can ventilate the space below the building to reduce the concentrations, then even if the pressure goes back and forth and some gas enters the building, if the concentrations are too low to be a concern, then it's really not a problem. So we can move forward to the next slide. We can look at the distribution of vacuum underneath the building and the flow velocities using mathematical modeling. You find in order to get to a target vacuum underneath the building of 6 pascals, which is recommended in the ASTM standard for radon mitigation, that, for a particular building, you might need flow rates of hundreds or many hundreds of standard cubic feet per minute. And even then, you might have some regions between your extraction points that don't quite get to the 6 pascal vacuum. But when we've done analysis of the concentrations that result below the slab, there's not necessarily a minimum concentration occurring at a condition of a 6 pascal vacuum, because if you start sucking hard enough, you can actually pull chemicals up from their source depth. So the ideal condition underneath the building is to be a little bit more gentle, create enough flow underneath to reduce the concentrations, but not suck so hard as to pull chemicals up from below. And as a result, use a much lower flow rate, much less energy. We've also developed systems for real-time monitoring and control, where we can monitor the vent pipe pressures and vacuums and have variable speed drives on the fans to increase them automatically if there's a particularly windy day where that's needed. Next slide. But what this also does is it creates an opportunity for more energy efficient and more sustainable options, including wind-driven and wind and solar-driven venting systems. And we've done about 5 or 6 years worth of research with this for the Army Corps of Engineers at a site in New Jersey. And we've been monitoring flows and vacuums in the pipes to establish the specific capacity of the pipe, and then monitoring just the vacuum in the pipe as a way to calculate the flows. Next slide. Where we know the wind velocity and we know the vacuum that's generated in response to that by the turbine. We can just measure the wind velocity and calculate the flow in the pipe. Next slide. If the wind isn't enough to create the suction that's needed, then a simple fan with solar power and a solar panel and a battery can augment that and keep things running at times when there might not be as much wind. Next slide. So I regret that we've gone about 7 minutes over, and that I had to hustle through some of the details of the interesting parts of the presentation in order to get done even by now. But I did want to mention the Vapour Intrusion team at Geosyntec has got a lot of the industry's top professionals, myself included, but Robbie Ettinger, Dave Folks, and Helen Dawson are all internationally recognized experts. And we have a number of people that would be considered company-level leaders at other firms. We've worked cooperatively with many other consulting companies in teaming arrangements to help transfer some of the technologies that I've described today, and more than happy to talk with anybody who's interested in finding out more about any of these things. For pretty much any of the topics that I talked about today, I could give a talk just as long as this one. This is really just an overview. And with that, I'm happy to take any questions.
Thanks very much, Todd. And if anyone has questions, you can either use the messaging system on the left of the screen, or just be sure to unmute your line if you're trying to ask. Well, you're gathering your thoughts. I will just mention again that we have recorded this webinar, and that will become available afterwards. We've sorted out the technology to take care of that, so I will provide details of that as a follow-up for anyone who wants to watch again or share with colleagues who might find it of interest.
Might also scroll ahead to the next two slides. What I've included is a list of what I consider to be useful reference materials.
Sure.
With
Todd, I don't know if you can see the public chat comments in the lower left corner. There's a couple of questions, one from Dawit and another from Giovanni.
Okay. So, as it is known, vapor intrusion is highly impacted with vadose-zone heterogeneity of soil stratum, soil moisture and temperature. Please update your views on this issue. Well, certainly moisture has a huge effect. Vapors can only diffuse through the air-filled pores in soil, and as the soil gets wetter and wetter, those vapors dissolve into the moisture and are diffusing through water. The aqueous diffusion coefficients are about 10,000 times lower than the gas-based diffusion coefficients, so there's a dramatic drop in the rate of transport in wet soils. Furthermore, rather than saying the word heterogeneity, I think what I'd rather use is the word stratification. So in cases where there are laterally continuous clay-rich layers, they can be acted as a very effective barrier. And they don't even have to be very thick in order to be able to do that, as long as they're continuous. Now, one of the most interesting and inexpensive ways to assess the potential presence is through measuring the pressure in a soil gas probe over time. If there is a barrier in the vadose zone, a deep soil gas probe will not always have the same pressure as the atmosphere. So if you hook up a pressure transducer, you'll see a signal that goes all over the place that's not just a zero gauge difference. Whereas if the entire vadose zone is gas permeable, then any change in barometric pressure will transmit quickly through the vadose zone, and you'll see differential pressure between the soil gas probe and the atmosphere. It's pretty much a flat line. So it's really not that difficult to demonstrate that there's a geologic barrier to vapor intrusion, although it's seldom done. The next question that I see is from Giovanni. What is your opinion on a possible starving problem the passive samplers can have? Oh, I'm glad you asked. Passive samplers are designed so that they'll take chemicals up from their environment at a certain rate. As long as the environment provides chemicals at that rate or greater, then the sampler itself is not going to cause a bias on what it's attempting to observe. But if the rate of supply is less than the uptake rate, then the sampler basically scrubs its environment. And as a result, the concentrations decrease. And as a result, the passive sampler doesn't have enough mass to maintain the rate of uptake that it should, and a negative bias results. Now, we've put a lot of time and effort into the passive soil vapor sampling, where that's a big concern because there's not really a lot of convection or advection or flow, and the rate of transport to the sampler is limited by diffusion through the soil. So we did a bunch of calculations to try to figure out what kind of diffusive supply rate would occur, and then design the passive samplers to have an uptake rate that's lower than the supply rate. And now we get quantitative passive soil vapor sampling, and it works quite well. So I see another question from Julie. Would aerobically biodegradable constituents like vinyl chloride behave similarly to BTEX and soil gas? They should. I would like to be able to say that with more confidence, but the truth of the matter is there have not been very many sites where there's been enough vinyl chloride that convincing data sets have been collected, and we've been looking for those. There are sites where vinyl chloride is present in groundwater, not so many where it's present in soil gas, and very few where it's actually the driving factor of risk in indoor air. So that is consistent with aerobic degradation, reducing their concentrations below levels of concern. And there's some papers that have been published that show that that process occurs. Not very many vapor intrusion cases that have detailed data on it.
Okay, do we have any more questions before we wrap up today? Oh, I see one from Sarah has just arrived.
Yeah, sorry, I was halfway through reading Sarah's question when the next one came along, and it got me off my, how much groundwater remediation by pump, treat, or sparging encourages production and release of vapors? Okay, so if you're doing groundwater extraction, then you create a drawdown cone. That lowers the water table. If you lower the water table, the zone that used to be saturated is now unsaturated, and their continuous gas phase will develop. But the pore moisture that's left behind could still be containing VOCs. And so they now have a continuous gas phase to vaporize into and can migrate through. So it'll depend largely on how much drawdown occurs. Now, some groundwater pump and treat systems are designed so that they aggressively lower the water table. That can happen, for example, where there's an elm apple and you want to expose it to the gas phase because it can be remediated more rapidly through soil vapor extraction, for example. But if there's not also vapor extraction or bioventing going on, then it could actually increase the risk of vapor intrusion, and it maybe even more so if it's chlorinated compounds. So then Dawit said stratification is when there's continuous thing or soils. When there's discontinuous soil stratification, do you consider the relevancy of 2D or 3D numerical modeling of vapor intrusion? Well, this is where modeling sometimes breaks down. The models are often based on simplifying assumptions like uniform, homogeneous, isotropic, one-dimensional, or whatever. In the real world, those often don't apply. If you have stratification, but it's discontinuous, and there's a pneumatic connection around the edges of the discontinuous strata, then the deeper soil gas probe pressures will still track closely with atmospheric pressures, and so that differential pressure monitoring is still a useful technique to tell you whether there's isolation or not isolation. One thing that's interesting is, I didn't mention this earlier, that pressure transducers can measure a difference as low as 1 Pascal. Barometric pressure, which is 101,000 pascals, can vary by up to 3% per day, which is 3,000 pascals. So the magnitude of the change in the signal compared to the sensitivity of the instrument is huge. So using the pressure transducers to monitor the deep probes provides usually a signal that can be resolved and can also be interpreted if you know something about the permeability and stratification of the soil from borehole logs or other such things.
Okay, do we have any further questions for Todd before we wrap up today? If not, I'll just say once again, on behalf of Geosyntech, thank you very much for your attendance today. And Todd, thank you very much for staying up very late Canadian time to deliver this presentation. It's been an excellent presentation, and thank you everyone for bearing with us on a couple of technical difficulties, and apologies for that. Always learning something new about this software as we go, so we will again look into that prior to our next meeting. We will plan to hold another webinar in the first couple of weeks of October with topic and exact date to be determined, but we will keep in touch with everyone. I will send you a follow-up email just to get any insights or comments or other on the webinar experience all around, any suggestions or comments you might have. And of course, as soon as the recording of this webinar is available, I will distribute a link to anyone who is interested. And I will also include a link if you think any of your colleagues would be interested in attending future webinars or having at least receiving the announcements of the webinars. I will send a link as a way to join our mailing list, and feel free to forward that to any of your friends or colleagues who might also be interested.
Well, thanks again, Lang, for putting this on.
Okay, well, thank you, Todd. And with that, so we will close the meeting. And thanks again, everyone, for attending.